Now we will focus on Arctic region. So we will look at what are the halogen sources in the Arctic region. Sea ice and snowpack, that is release of halogen during sea ice formation and melting happens. What is the process? Photochemical reactions on the surface releases reactive halogens. And what are the other anthropogenic sources? Industrial activities and shipping emissions leads to release of halogens. They contribute to local halogen levels, and there is also volcanic activity. Occasional volcanic eruptions also release halogens. Episodic but a significant halogen source. Let us look at the halogen chemistry in the Arctic region. One is ozone depletion that we have seen so far. The halogens catalyze the breakdown of ozone molecules, more pronounced in spring due to increased sunlight, and there is a significant ozone depletion observed in the Arctic stratosphere. And the next one is the bromine explosion reaction. Here sudden release of bromine from the sea ice leading to the high levels of reactive bromine. There is a rapid and significant depletion of surface ozone, and this is frequent during polar sunrise. And the next one is another important thing, which is mercury deposition. The reactive halogen converts gaseous mercury to particulate form, which deposit onto the surface. This increases the mercury contamination in the Arctic environment that we had seen bioaccumulation and biomagnification. Those things we had studied earlier in the contaminant module. So higher mercury deposition rates are observed in the Arctic region. There is also another important class of compound called volatile organic carbons. So we will be just briefly looking at what are they. These organic chemicals that have higher vapor pressure at room temperature are called volatile organic carbons. The main sources in the Arctic is basically vegetation and ocean emissions. Of course, we also have fossil fuels and industrial process which release volatile organic carbons. What is their influence on the Arctic when we look at the atmospheric chemistry? The interaction with the nitrogen oxides forming ozone is the main contribution, and they are also contributing to secondary organic aerosols. And what is the impact on ice? The deposition on they deposit on the ice surfaces, which alters the albedo effect. And how do we know that? We can identify the concentration using there is increased VOC levels due to human activities. And ozone formation, that is the elevated ground level ozone affecting the Arctic health that we had seen for the human population. And how do we know all these things are happening? We can do the air sampling and remote sensing. So what is the importance of volatile organic carbons and halogens? Volatile organic carbons and halogens contribute to the formation of ozone, aerosol and other pollutants in the troposphere. The chemical reactions involving VOCs and halogen can alter the properties of Arctic ice, which leads to melting process. And what is troposphere? Very basic information about troposphere. This is the lowest layer of Earth atmosphere. And what is the characteristics? It contains 75% of atmospheric mass. Weather process mainly occur in this particular region. Tropospheric temperature influence the ice melt and formation, especially in the Arctic region. The pollutants are basically transported to the Arctic, which affect atmospheric chemistry. So that is the major reason troposphere is causing changes to the Arctic region. Similarly, Arctic warming twice as fast as the global change is the trend we are actually observing. Similarly, the increased level of pollutants like black carbon and ozone are being deposited in the Arctic region. We can study all these things using weather stations and remote sensing. What is the climate change mechanisms and the pathways? Basically, there is one thing called the feedback mechanism. Ice albedo effect. Basically, the melting of ice reduces the reflectivity, which increases absorption of solar radiation. So, when solar radiation is there, that is actually responsible for the many of the halogen chemistry. Similarly, pollutant depositions, especially VOCs and halogens, alter the ice melting rates. And what is the pathways in the atmospheric change? There is an increased greenhouse gas and the pollutants in the troposphere. Similarly, what is the oceanic change? There is a warmer sea surface temperature affects the ice stability. And how do we know all these things? There is a change in the sea ice extent from 1980s. The sea ice was around 7.5 million square kilometers in September, which had reduced to 3.9 million square meters in the September of 2020. So there is a drastic reduction. Roughly half the amount had been gone. The sea ice had been gone. Similarly, there is a temperature anomalies. Arctic is warming twice as fast as the global average. That is what we had seen in the Arctic amplification. Roughly 3 degrees centigrade had increased since 1970. And what are the different models which are used to predict what the changes? One is the GCM, that is general circulation model. Here we simulate the climate dynamics over large scale. Another one is chemical transport model. Here we focus on atmospheric chemistry and pollutant transport. The third one is regional climate model. Here we focus on specific regions for detailed analysis. Only few are given, but there are also other methods which can be used. Similarly, the predictions made by all these models include temperature increase, sea level rise. And other models include chemical transport model. Here they simulate the transport and transformation of VOCs and halogens in the troposphere and their interactions with the Arctic ice. The climate model incorporates VOC and halogen to assess their contribution to Arctic climate change and ice melt. The ice models integrate chemical process into models in Arctic ice dynamics to investigate feedback mechanisms. So how do we study all these things? We can do field studies like ice core analysis or air sampling. We can also do remote sensing. We can carry out satellite observations, laboratory experiments, and we can also carry out climate modelings. So what are the different techniques used or employed to measure the reactive halogen species in the troposphere? One is lithium hydroxide impregnated filters can be used. The second one is mist chamber techniques. Third is atmospheric pressure ionization mass spectroscopy. We will be just looking at some of the methods. Chemical ionization mass spectroscopy, denuder sampling, and inductively coupled plasma mass spectrometry, that is ICPM. Then we can also use ultraviolet and UV vis spectroscopy. So here differential optical absorption spectrometry, cavity ring down spectroscopy, and fluorescent techniques are the methods which use UV and visible spectroscopy. So what is API-MS, that is atmospheric pressure ionization mass spectroscopy? This technique is mainly employed to measure the tropospheric chlorine, bromine, and bromine chloride species. The sample was introduced into the discharge region where air forms ions with O2 minus with electron affinity of only 0.45 electron volt. Species such as chlorine, bromine, and iodine with the electron affinities higher than the O2 minus accept an electron from O2 minus, generating the molecular ion of interest. So this way we can actually, if chlorine is there, then this reaction occurs. If chlorine is not there, this reaction does not occur. So the detection limits of halogens are up to the order of 1 ppt. The next method what we can use is chemical ionization mass spectrometry. So here it makes use of the ion molecule interactions to selectively ionize the compounds of interest in the sample. It is very specific and has a fast response, and the detection limits are of the order of few ppt, that is parts per trillion. The disadvantage is like the air samples are introduced into the instrument through sampling inlets. This leads to possibility of losses and reaction of the species of interest on the inlet surface itself. DOAS is one method we had mentioned earlier. So differential optical absorption spectroscopy basically works on the different gases absorb light at a specific wavelength. So based on that, when sunlight or another light source passes through the atmosphere, certain wavelengths are absorbed by the trace gases. From that, whatever is the loss, we can actually find it out. Those gases are actually present. So a spectrum of transmitted light is basically recorded. The spectrum shows the range of wavelength, including those where specific gases absorb the light. The differential absorption means the technique focuses on differential absorption features by comparing the measured spectrum to a reference spectrum. The absorption due to specific gases can be isolated. So we use Beer-Lambert's law as the mathematical analysis, and we can also use it for multi-gas detection.